coming out. So as many of you know, I've been running a working group on Wednesdays this term on the general topic. So this talk will be partially a recap of what's happened so far, which it'll be pretty similar to the talk I gave at the beginning of that series of meetings. But by the end, I'm hoping to get to a preview of what we're going to be talking about, or what I'm going to be talking about in the next couple of weeks in that group. So some things that happen in the end that are very sketchy will be fleshed out in more detail in those talks. So throughout this talk, K will be a finite field. And I'll use the letter P to denote its characteristic. So I might write Q occasionally for the cardinality, which is, of course, the power of P. And X is always going to be a smooth variety over K. So it'll be something which is locally an intersection of hypersurfaces whose gradients are linearly independent. And so, well, in general, when you have a variety not necessarily smooth over K, you can associate it to its zeta function. This is a fundamental construction that at this level of generality goes back to V. So just like the zeta functions one encounters in number theory, like the Riemann zeta function or Deligne zeta functions, it's formed as some sort of Euler product. But this time, instead of, say, prime numbers or prime ideals, the corresponding thing to index over are closed points of the scheme X, or equivalently, if you look at points over an algebraic closure of K and you take orbits under the Galois group, those are in bijection with the closed points, so you can kind of translate into that language, but this is the more typical one. So this Euler product consists of a factor for each closed point, which is some sort of inverse characteristic polynomial, or Fredholm determinant. Sorry, that's when I get to the trace formula. Right now, it's just a product of terms, each of which detects it detects the degree of X over K, meaning, well, the residue field of X is some finite extension of K. So this is the degree of that field extension, or in the language of Galois orbits, this is the length of the Galois orbit corresponding to this point. So this varies, and the fact that this factor varies is sort of analogous to the fact that when you form the Riemann zeta function, you have 1 minus p to the minus s, and so it's the p that's varying. This is, if you were to write, if for t you were to put q to the minus s, this would look much more like a Deligne zeta function, and you can even make a common definition for schemes of finite type of the integers, but never mind. This is the expression I'm going to work with, and a priori, I want to think of this as a power series with integer coefficients. I should mention, for the sake of completeness, that when one actually tries to, say, compute examples by hand, you don't generally use this expression. You use this other expression, which is not a priori integral, but is a little bit easier to do computations with. So if you count the number of points on X with values in every possible finite extension of K, then if you put these into a generating series in the right way, it will give you back this expression. So this is an easy exercise to compare these two things. And so this zeta function carries a lot of important information, and many questions that come up in number theory have something to do with this, including even in applications. For example, if you talk to computer scientists who do cryptography, they will sometimes have to deal with elliptic curves over finite fields, or sometimes even the Jacobian of a higher genus curve over a finite field. And then to know what finite group you get when you, say, take points, that information is, well, some of the information about that, like the order of that finite group, is tied up in the zeta function. So now, how do you actually get any information about this thing? Well, the paradigm for gathering information about this thing is to give it a spectral interpretation. And this, of course, is related to, I mean, this was introduced by way of analogy with things like the Riemann zeta function with some hope of gaining insight about, say, the Riemann hypothesis that could be then transferred back to the number field case. That maybe has not happened as to the extent that one would have liked, but this idea of a spectral interpretation is certainly something that one looks for in the number field case. But here, it'll turn out that we have it. So what do I mean by a spectral interpretation? I mean some kind of Lefschetz trace formula. So the idea is to interpret via Lefschetz trace formula, right? So the points on x with values in fq to the n can be thought of as the fixed points of the nth power of the absolute Frobenius acting on x, right? Because we're in characteristic P, raising everything to the q power is a field, it's a ring automorphism for any ring of characteristic P. And so in particular, it defines so f, maybe I should write f sub q to mean the q power Frobenius is some automorphism of x, which is k linear because I'm taking q rather than p. And so that acts on x. So if you have some way to, so to speak, linearize x by, i.e. if you have a cohomology theory, then you could hope that you could interpret this thing as, and this is just what you get by exponentiating the usual additive form of the trace formula. You would like to interpret this thing as some kind of product of, now these are inverse characteristic polynomials. And to get this exactly right, I need to put some factors in. So this is q to the dimension of x times f inverse times t. So f will be some automorphism of some vector space. And here, sorry, that might be out of view. So I need to put plus or minus signs in the exponent because this thing in general is only going to be a rational function, not a polynomial. OK, so I have so what I'm looking for is some expression of z as, this is going to be some finite dimensional vector space. Maybe I should write fq here for consistency. So here I have some finite dimensional vector space over some field k of characteristic 0. And I have this thing is supposed to, so this construction, the operation that associates x to this hi of x should be a contravariant functor. So in particular, I could take the action of Frobenius on here, and OK, never mind about this. This is just some normalization. But up to some normalization, I'm looking at the characteristic polynomial of Frobenius on this vector space. And this, depending on the parity of I, this contributes to the numerator or denominator of the product that I get here. So for example, if x is an elliptic curve, it's been known for some time that this thing has the form, this observation goes back maybe to Emil Artin, that this expression looks like this. You have a denominator of 1 minus t, 1 minus qt. So this will come from h0. This will come from h2, whatever that is. And this is supposed to come from h1. Of course, I haven't told you what these things are yet, but that's the way you're expecting things to match up from, because we know what the form of the answer is in this case, and so you're expecting that these contributions, right? So this minus 1 to the I plus 1 gives you, puts you is negative for I equals 0. So the even indices contribute denominators, the odd indices contribute numerators. Okay, so this of course would imply, this will of course imply that the xt is a rational function, or maybe it's better to say it's a power series representing a rational function, but let me conflate them and just say it is a rational function. And yeah, there's more. Of course, there are more things we can say. So for example, there's a theorem of Hasse that tells you that the absolute value of A is at most 2 times the square root of Q, which means that this thing has a pair of complex roots instead of real roots. And in particular, those complex roots have absolute value Q to the minus a half. Whereas, so that tells you exactly what all the complex absolute values of the zeros and poles are, because here you have a root of complex absolute value 1. Here you have a root of complex absolute value Q to the minus 1. Here you have Q to the minus a half upstairs. And that's not an accident, of course. That's somehow some analog of the Riemann hypothesis, which is included in the Weil conjectures. But we won't actually see that much of the Riemann hypothesis part of the Weil conjectures in this talk. So let me not dwell too much on it. It's, of course, hiding in a lot of the calculations. But OK, so of course, the zeta function is an interesting invariant, which we would like to be able to understand. And it turns out, so one also wants to understand the variation of the zeta function in families. So for i.e., you want to consider the fibers of smooth morphism. Say you have some f from y to x. Right? So this is like some family of smooth varieties parameterized by some base. For each fiber, you can consider the zeta function. And one would like to be able to understand how the zeta functions vary as you vary the parameter. So for example, you can look at the universal family of elliptic curves over a modular curve. Say like x of n or something, or x naught or x1, whatever, some modular curve. The middle coefficient. Right? There's only one coefficient that doesn't depend just on Q. So the A is somehow the interesting parameter. And you'd like to be able to understand, as you vary over elliptic curves in some family, what can you say about how this thing varies? So obviously, I told you this theorem of Hasse that says that the absolute value of this integer is bounded by 2 root q. But can you say anything more useful than that? OK. And it turns out that it's important to be able to say things more useful than that, because this is, in fact, one of the tools for proving the Weil conjectures is to be able to work in these families. So of course, now I get to the point where I actually talk about actually, let me do it on this board so I don't take up as much space. So, right, so this paradigm was proposed by Weil, that you should interpret zeta functions in terms of some kind of spectral interpretation, some side of cohomological construction. And it turns out there are basically 2 strategies that can do this for you. One of them may be more familiar than the other. So roughly speaking, there's an analogy with singular cohomology, right? Cohomology of topological spaces built out of kind of looking at simplices. And there's another one, this is the maybe less familiar one, which is constructed by analogy with de Rham cohomology, looking at the behavior of differential forms. So the analogy with singular cohomology is what turns out to lead you to Etale cohomology, as it was introduced by Grothendieck. So this was initiated, the study of Etale cohomology is initiated by Grothendieck, and then many people, including Deligne, added key components to it. But it turns out that, for example, if you just isolate the question of proving that zeta function is always rational, of course, one proof of this is to establish the Lefschetz-Trace formula for Etale cohomology, and then also check that Etale cohomology gives you finite dimensional vector spaces over, say, QL, although for uniformity, I want to work with an algebraically closed field of characteristic 0. So you can think of Etale cohomology as giving you QL bar vector spaces for any prime L except for L equals P. Something goes wrong with L equals P that maybe I won't sweat too much right now, but there's some basic geometric reasons why L equals P doesn't work. For example, if you look at torsion of elliptic curves in characteristic P, the L torsion behaves differently than the P torsion. Somehow the L torsion behaves like characteristic 0 and the P torsion doesn't. So that's a sort of symptom of what goes wrong when you try to take L equals P. So Etale cohomology gives you vector spaces over some L-adic field. And yeah, so if you get through, say, SGA4, you eventually prove that there's a Lefschetz-Trace formula involving these finite dimensional vector spaces. And that gives you that this is a rational function. But it turns out that this rationality was established a few years earlier than that by Dwork using methods of P-adic analysis. Well, so in Dwork's work, the field K, if I were to interpret it in this language, it would be an algebraic closure of QP rather than some QL. And so, so various people, so Dwork's proof was not written in the language of cohomology. Dwork did not explicitly give a spectral interpretation involving finite dimensional vector spaces. He had some kind of infinite dimensional P-adic spaces with some carefully constructed topology, and that gave him enough information to do this. But it turns out you can reformulate Dwork's work in the language of, in a more cohomological language. So this somehow is done by combining ideas of Monsky-Waschitzer, who understood how this worked for smooth affine varieties, and then Grothendieck contributed largely via his work with Berthelot, contributed a good understanding of what to do about proper varieties. And then Berthelot put this all together. So the proper version is what's called crystalline cohomology. But Berthelot's ultimate theory is called rigid cohomology. So rigid cohomology is the sort of Weil cohomology with P-adic coefficients that applies to not even just smooth varieties, arbitrary schemes of finite type over a finite field. But I'm only going to talk about the smooth ones. So this is some kind of reinterpretation of Dwork's P-adic analytic proof of the rationality of the zeta function. And so it turns out there's kind of a whole parallel picture that goes along. So for example, you can ask, well, is there some kind of object, if you have a family of varieties, so in a family, so given a family of varieties, like so, are there objects, so to speak, on X, whatever that means, which interpolate the cohomology of fibers? So is there some way to define some kind of category of objects attached to X which which can be pulled back along morphisms, and such that if you were to say pull back from x to a point, you would get the cohomology of the fiber. And so these things, you have these things in both these cases. So here you have some sort of Etale local systems, which one way to say what they are is to say that they're continuous representations from the Etale fundamental group of X in the sense of Grothendieck. So this is some analog of the ordinary topological fundamental group thought of in terms of covering space morphisms, except instead of arbitrary covering space morphisms, you're only allowed to use finite covering space morphisms because the infinite ones don't make sense in algebraic geometry. And so you have continuous representations from this group into some matrix group over this K, QL bar. And so the point is that this thing, for every closed point, you have, so you can, of course, restrict to, maybe I should say it this way. If X is a closed point, right, you can think of the closed point as a scheme in its own right. And you can, as I said, this construction is functorial. You can restrict, it's, I guess, covariantly functorial. You can restrict the fundamental group from the fundamental group of X to the fundamental group of little x. And this thing is this is profinite generated by right? This is basically the Galois group of a finite field. So the Galois group of a finite field is profinite on a distinguished generator by the Frobenius sort of associated to X. So that means when you restrict one of these things to a point, you have basically what you have is a vector space. You have a finite dimensional vector space over QL bar plus an endomorphism. Okay, and that's the setup that you need for the spectral interpretation. So in this P-adic world, there is, again, a notion of local systems, but this is more of a de Rham version. So these the objects that you get are called overconvergent F isocrystals. I'm not going to try to give you a formal definition of these things, but just to say briefly, these are some sort of vector bundles with, so this is like the opposite side of the Riemann-Hilbert correspondence. So instead of looking at local systems, I'm going to look at vector bundles with flat connections. And then I also need some kind of Frobenius action. This corresponds to the fact that here, note here that I'm taking this is the fundamental group of X as a scheme over a finite field, not X base change to an algebraically closed field. That would be the geometric pi1. So if I were talking about geometric pi1 over here, that would correspond to like vector bundles with a flat connection. But this thing is bigger by somehow the geometric pi1 plus the Galois group of the base field. And so adding that is like adding this Frobenius action, which somehow has to be compatible with the other structure. So maybe I should draw this exact sequence here. So here I'm implicitly referring to an exact sequence like this. So pi1 of X base change to K bar is a subgroup of pi1 of X, because this maps to this. And then this in turn maps to pi1 of spec K. Again, because X maps to spec K. This is the absolute Galois group of K, which is a profinite group Z hat, and with this Frobenius as a distinguished generator. So this picture is like vector bundles with flat connection are like representations of this group. And then in order to promote them to representations of this, I need an action of, well, I take some section of this. So I take an element in here which acts like this. I need that to act, but I need this to be compatible so I'm getting the right extension. So writing down vector bundles with flat connection is in some sense relatively easy. Adding a Frobenius action is quite restrictive. And this sort of explains the conjecture that I'm about to state, which says that both these objects and these objects are relatively scarce. They somehow can only exist for arithmetic reasons. And again, sorry, but I didn't say where these live. These live on these don't live on x because I want something that happens in characteristic 0. Right? If I gave you a spectral interpretation in characteristic P, that wouldn't tell you so much because that would only tell you that this thing looks like a rational function mod P. But it's actually, I mean, it's really a power series with integer coefficients. And so I don't want to be stuck in characteristic P. So the way you get out of this is you don't work directly on x. You work locally, you work on a smooth lift of x. And well, not in an algebraic sense, but in some sort of rigid analytic sense. So for example, if you were starting with the affine line, what I'm telling you here is not to work with, well, you could lift it to the affine line in characteristic 0, but what I really want you to do is take a formal lift and then take the generic fiber of that. So that would correspond to, like if you start with the affine line over fp, what you get at the end of this process is a closed unit disk in the rigid analytic affine line over qp. So you don't get a scheme. This lift is not a scheme. It's some kind of P-adic analytic space. But again, it makes sense to talk vector bundles with flat connection. So, and when you do this carefully enough, you get something which is actually independent of choices. So this somehow depends on the fact that two lifts of the same thing out of characteristic P might not be isomorphic, but in some sense you should think of them as being deformation, like homotopy equivalent. If they have the same reduction mod P, they're in some sense close to each other p-adically, and that lets you deform at the level of cohomology from one to the other. Okay. Okay. Right, and as I mentioned, in both of these cases, like in this case also, if you take a point, then the lift that you take is just, will itself be a point. It'll be a point over k. And so a vector bundle with flat connection on a point is a vector space. And then it has this Frobenius action. So again, you're getting, at a point, you're getting a vector space with a linear transformation. So it makes sense to look at one of these things. So I'm going to refer to these things as coefficient objects in one category or the other. So if E is a coefficient object, so these are the things that are supposed to record kind of cohomology. I mean, they're constructed so that they are able to record cohomology of fibers in a family. But a priori, they're just some objects you in principle could construct without reference to any family. So it's a question whether or not these things actually necessarily come from some geometric situation. But before I address that point, let me make this definition. If E is a coefficient object, then I want to talk about So I have a function that takes closed points and spits out polynomials, which is to say for every closed point, I look at the fiber of this thing at the point. So I pull back to the point and I interpret this as a vector space with an endomorphism. And then I take the reverse characteristic polynomial. Okay. And of course, you can make an L function out of these by analogy with the definition of the zeta function. I don't think I'm going to use that right now, but you should. If you should be thinking that these things have L functions associated to them, which then have, again, a spectral interpretation in terms of the sort of cohomology with coefficients in this E. That's why this is called a coefficient object. No, I still have a board. OK, so now I can tell you what this conjecture of Deligne is. That's the main subject of the talk and of the seminar, of the working group. So it says, roughly, that these coefficient objects don't exist by accident. They basically, well, we know one way to produce them, which is to consider families of smooth morphisms and take the sort of relative either Etale or rigid cohomology. So this is not formally stated as a conjecture, so let me call this an expectation, but it motivates the following conjecture. Coefficient objects should only exist for geometric reasons. That is to say, the definition of a coefficient object, because of this compatibility between, in this picture, between this geometric fundamental group and this Frobenius action, or here between the connection and the Frobenius action, this interaction is so fraught that it's hard to actually make those things compatible unless there's some geometric reason that they're forced to be compatible. Namely, there's some family of varieties that actually produces that as relative cohomology. Yes?
This capital X, is that a capital X or a small?
This is a small x. So it's just, right? So what I'm saying is, for every closed point, if I restrict from x to that point, then as we said, the corresponding object that you get here is just a vector space with a linear transformation. So I'm just recording sort of the only real data I can record from that is its characteristic polynomial. I'm not attempting to record, if this thing is not semi-simple, I'm sort of discarding that information. Because, the information, right, because what's relevant, if you do take the L function, this is what you feed into the definition of the L function. So this is somehow the only thing that is really meaningful and variant. And so this conjecture of Deligne says, in fact, that this function is basically, if you sort of sort these coefficients by this function, well, it says the following. So for E, a coefficient object, so in order to make this statement rigid, I have to sort of rule out the possibility of kind of twisting by a rank 1 object that breaks the statement. So I'm going to assume this is irreducible and its determinant, right? Determinant just means you take the top exterior power. So E has some rank. So you take the exterior power of that rank to get something of rank 1. So I'm going to assume that this is a finite order, meaning this is rank 1. So if I take tensor powers of it, those are still rank 1. So finite order means that this rank 1 object, some tensor power of it is the, so to speak, trivial object. So there's always a trivial object. Here, you take the trivial representation. Here, there's a trivial, right? You take n equals 1, and you have a trivial representation. In this context, right, there's a trivial rank 1 vector bundle, namely the structure, the one coming from the structure sheaf, which has a flat connection, and you can put a Frobenius action on that. So I'm going to assume that E is irreducible and its determinant is a finite order. This sort of makes E sufficiently rigid that the following two things are expected to be true. That, first of all, these characteristic polynomials are not just polynomials over K. They're actually polynomials over Q bar. So they actually potentially mean something from the point of view of zeta functions, right? Because for zeta functions, of course, the zeta function, right, I'm giving the spectral interpretation in terms of some very large field, but the answer is supposed to be a rational function with integer coefficients. So in order for something to show up as a factor of a zeta function, if you normalize the constant term to be 1, then it actually has to have Q bar coefficients. So this is telling you that this thing could actually show up. This thing could actually exist for a geometric reason in the sense that it appears in the zeta function of a fiber of. So it appears as some consistent factor in the zeta functions of fibers of some morphism down to x. So this is supposed to be a consequence of just having these rigid properties. And the other thing is that these things don't exist in isolation. So for any other choice of k, say for any other k prime, and any choice of isomorphism between, if you have k and k and k prime might be different, might involve different L's. One might be L-adic, one might be P-adic. They have nothing to do with each other, But if I look at the q bars inside them, of course, there's only one possible algebraic closure of q up to isomorphism. So I can choose some isomorphism between the q bars. And so now that I know that these things live in q bar, if I have these things inside k, and I look at if I look at a coefficient object, maybe I'll call it a k prime coefficient object, e prime, then what I expect is that so this was for all closed points, and this is again for all closed points. Right? So and such an E prime is called a companion. So the companion relation says that the characteristic polynomials, right, I can compare these things because they both live in q bar, in their respective q bars, and I fix the isomorphism between those q bars. So it makes sense to ask whether these two polynomials have matching coefficients. And so I'm saying for any choice of the isomorphism, I get a choice of the object that does this. So for example, this already has content if k equals k prime, but this is a non-trivial automorphism of the q bar inside. This is saying that there's some kind of Galois conjugate. And that's non-trivial in case, yeah, if you're looking at an automorphism of q bar that does not fix the particular place above L that defines this embedding, then this is saying that when you apply that non-trivial automorphism to traces, there is some other object that corresponds. So it really has content already in that situation. But of course, I'm mostly going to be focused on moving between primes, especially moving back and forth between the left-hand and the right-hand sides of the board. OK, so this is, of course, a reasonable conjecture if you believe this conjecture, because if this is true, if you have an object that exists for geometric reasons, because, well, yeah, I mean, with some effort you can show, because if you have a family of varieties and E appears inside the relative cohomology of that, well, you can form the relative cohomology with all possible types of coefficients, and then with some effort you can match things up to see that there is a piece with the other field that matches up with this one. It's not completely straightforward, but you can do some work and show that works. So you sort of expect that, I mean, maybe if you're optimistic, you expect that coefficient objects exist for geometric reasons. This statement is kind of hard, as I'll show you. We only really have traction on this statement when x has dimension 1, and maybe a few other cases. But it's plausible, and so that makes this conjecture reasonable, right? This conjecture, I should mention that this is one of the unresolved points from Deligne's V2 paper, where, of course, he resolves a great many things. I should also mention some more kind of down-to-earth consequences. So if E is an Etale local system, the existence in particular of a crystalline companion, and crystalline I'm just going to mean as a shorthand for taking k to be qp bar. So knowing the existence of a crystalline companion tells you, looking for more Hakaroma here. All right. So this tells you a lot of concrete things about these characteristic polynomials. So for example, it tells you that these characteristic polynomials can have only finitely many normalized Newton polygons as x varies. So let me make some space. to give you an example of this. So to show you that this is a non-trivial assertion, let me show you what this says in the case of elliptic curves, which may be a familiar statement, but if you haven't reflected on it, you might not have realized that it's actually a highly non-trivial statement, because we kind of think of it as sort of second nature. So, e.g., so if I have a family of elliptic curves, or say over some modular curve or something, for each fiber over, say, an fq to the n rational point, the zeta function has the form. So remember, right, there are only finitely many points with any given residue field. So as I look at different fibers, the power of q here is going to vary. And this value of a is also going to vary. And so now the idea is, what happens when you look at, if you look at the algebraic numbers that appear as the roots up here, well, I already told you what their Archimedean absolute values are. If you embed these, if you take roots of this in the complex numbers, you get two roots whose absolute values are q to the minus n over 2. It's also easy to see, because this is only divisible by p, that the L-adic absolute values of this are going to be trivial whenever L is not p. So the interesting question is, well, what can the P-adic absolute values of these roots be? Well, there's two options for if you fix a P-adic absolute value. So you fix a P-adic absolute value in q bar, then there's two possibilities that can occur here. One is that one root has valuation 1, has absolute value equal to 1. This is what's called the ordinary case. This is somehow the generic situation. And the other possibility is that both roots have the same absolute value, which is the absolute value of q to the power minus n over 2. Right, here one root has absolute value 1, the other one is going to have absolute value, the absolute value of q to the power n, minus n, sorry. And this is what's called the supersingular case. So if you look at a modular curve, all but finitely many points are going to be ordinary. There are going to be finitely many points that are supersingular, but nothing happens in between. So I think it took me a long time after I learned about the difference between ordinary and supersingular elliptic curves to appreciate the fact that this is a non-trivial statement, that there are no intermediate possibilities here. And this is not something that I would know how to prove using kind of Etale cohomology. But it turns out to be a relatively easy thing to prove using crystalline cohomology. So the behavior of Newton polygons is something that really you can only hope to get a hold of using crystalline cohomology. And you know a lot more. So you have a locally closed stratification by Newton polygons. So this is theorem of Grothendieck and Katz. So Grothendieck proved that these Newton polygons sort of increase under specialization, and Katz showed that the strata are locally closed. You also have some sort of purity theorem that says that jumps only happen in codimension 1. That was proved by de Jong and Oort. And again, these are statements entirely in the P-adic world. You can't really hope to prove them L-adically, but if you have a crystalline companion, then of course they tell you statements about the characteristic polynomials that you started with. There are more interesting things that are true. So you can control what are called pure slope L functions. So Dwork conjectured at some point that if you look at well, let me say it in modern language. If you take an Etale local system, you fix a p-adic absolute value on q bar, and for each factor of the L function, you pick out the contribution coming from roots with a particular p-adic absolute value. That's no longer going to be a rational function, but Dwork conjectured that it's a p-adic meromorphic function. It's a ratio of two entire p-adic power series. And that was proved by Da-Ching Wan around the year 2000. And of course, it's a very intrinsically p-adic argument. You can't hope to do something like this without using p-adic techniques. But of course, it's a statement that you can formulate starting with an Etale local system. And it's known to be true if you have a crystalline companion. So a lot of the interesting number theory about these things, somehow because the only interesting absolute value on these numbers turns out to be the p-adic ones, the Archimedean ones and the L-adic ones are kind of you sort of know exactly what the absolute values are supposed to be, but the p-adic ones can vary. So this is somehow where a lot of the arithmetic of these numbers sits. And in order to get hold of that arithmetic, you need p-adic techniques. I should maybe mention one other statement. For those of you who were at the working group last week, we heard about a form of p-adic Griffiths transversality, which says that if you consistently have a large gap between sort of consecutive valuations of in these factors, that actually forces E to split non-trivially. So this is a theorem of myself with Drinfeld. And last week, Joe Kramer-Miller gave us a talk about his alternate proof of this. So that's a sort of a short summary of different things that you could do if you actually knew the existence of these companions. There are other things you can do that are a little bit more advanced. So right at the beginning of the semester, we had a talk from Raju Krishnamurthy. He's working on a project that actually aims to use crystalline companions to show that in certain situations, the coefficient objects actually do exist for geometric reasons. I don't want to say much more about that because it's still work in progress. But that would be a particularly exciting application if you could actually use the fact that you can get to crystalline things to actually get back to geometric origins. OK, so let me, since my time is dwindling, let me just say a couple of words about dimension equals 1. And then you spend the rest of the time talking about how the dimension 1 case gets applied. And obviously, more details are to be found in the Wednesday talks. So in the case when dimension equals 1, you have the Langlands correspondence for function fields, for GLN, I should say, over the function field of x. So the Langlands correspondence, let me not write this on the board, but the Langlands correspondence for GLN tells you that rank n, well, I'll write this side on the board, rank n coefficients on x with, say, irreducible with determinant of finite order correspond to some sort of automorphic stuff. Right, so if you take irreducible with finite determinant coefficients of rank n, they correspond to cuspidal automorphic representations of GLN with finite central character, and they should be unramified on x. And Frobenius eigenvalues, so for Frobenius corresponding to some point, it's the eigenvalues of that Frobenius correspond to eigenvalues of some Hecke operator corresponding to that point. So that's sort of what distinguishes this bijection. This is not meant to be some sort of functor. It's meant to be a bijection that's somehow uniquely specified by matching spectral data here in terms of Frobenius eigenvalues with spectral data over here in terms of Hecke eigenvalues. OK, that's a sort of a deep story. The relevant part for this talk is that this side does not depend on k, does not depend on capital K, does not depend on what kind of coefficients you're talking about. So, but of course, the proof does depend on that. So I should say when L is not equal to P, well, maybe I should say first, when n equals 1, this is, of course, the Langlands correspondence is meant to specialize to class field theory, right? So this is a function field of transcendence degree 1, so class field theory applies. So for n equals 1, this is meant to be class field theory. For n equals 2, and let's say L not equal to P, this was done by Drinfeld about the same time as Deligne wrote his V2 paper. And the fact that this happened, I think, was some of the motivation that made Deligne willing to pose this conjecture. Drinfeld happens to be on campus today, so maybe a T. So for n greater than 2, Drinfeld's work was extended by Laurent Laforgue. I should say out loud that both of these works actually give you geometric reasons for this to be true. So you don't just prove a bijection. You also show that these coefficients, when you, in the process of doing this, you produce some explicit families of varieties where these things occur, these so-called moduli spaces of Stukas. So you get geometric origins as well as everything else you want in this case. And L equals P, I should say that, so this parallel I wrote on the board I wrote it as parallel, but if you think chronologically, then these boards become quite shifted, because while Dwork's work actually predates Etale cohomology, subsequent developments in P-adic cohomology have lagged behind Etale cohomology for various reasons that I won't go into right now. But the short version of this is that Laforgue's theorem appears in the early 2000s, and it wasn't until within the last year or two, well, the last several years, that the P-adic side of the picture had caught up enough that you could transcribe the proof into the P-adic world, and that was done by Tomoyuki Abe. So you need his work to go in either direction when you put L equals P over here. But for the purposes of this talk, everything behaves uniformly between L equals P and L not equals to P, even though the proof techniques are quite different. Well, the proof techniques are similar, but the technical details are quite different. OK, so let me, how many, I have like 7 minutes or something. So let me, so the theorem is that Deligne's conjecture is true. So let me break down the different components of that. So theorem, Deligne's conjecture holds. So for the purposes of saving time, let me focus on the second point. So I might say some words that are relevant to the first point, but let me focus most of the time that I have right now on this second point. If you want to hear about the first point, you can ask Daniel to re-give the talk that he gave in the working group. But so this second point, I want to break this down into 3 cases. Well, I'll call this case L to L prime, where these primes are different from P. So how do you go from one prime that's not P to another prime that's not P? How do you go from P to a prime that's not P? And how do you go from a prime that's not P to a prime that is P? And this is also the chronological order in which these were done. So this was done by, well, this is done by Drinfeld, but it builds heavily on ideas of Deligne. So let me put both of them here. This is 2012. This is done by Abe and Hainaut, and independently by myself. Let's call this 2017 or so. And then this is the recent work that I've been doing basically while I've been here. So these all use the same basic idea. The basic idea is that we only know anything about curves. So what you do, so the general strategy is to go from an L-adic coefficient to what's called a skeleton of L'-adic coefficients. and then from there to get to an L'-adic coefficient. So what do I mean by a skeleton? A skeleton is the following thing. So you have your x like this. So when I gave this talk a couple of days ago, I described this in terms of, I have a plate, and on this plate, so this is my x, and on this plate I have some large, massive pasta, say like linguine or some spaghetti or something, some sort of, pasta that comes in strands. So the point is that this picture, each of these represents a curve which maps to x. And if you need to be careful about these curves, there are various theorems of the sort of the framework initiated by Poonen that tell you that over finite fields you can sort of make generic constructions of curves just as if the field were infinite. But it's not so critical for this high-level overview what exactly you need the curves to do. So let me just leave the picture like that. So the idea is that if you have an L-adic coefficient, you can restrict it to any curve and then apply the Langlands correspondence to get, right, you go from an L-adic coefficient to the automorphic thing and then back to an L'-adic coefficient. And that gives you one strand of pasta corresponding to this curve C. And you can do that for every curve. Now, of course, this is not really enough data to assemble an actual L'-adic coefficient. But you have some additional compatibility coming from the fact that these curves can overlap. And when the curves overlap, you have the property that if you look at the two L'-adic things that you constructed on this point, and you restrict them to here, well, they are companions of the original L-adic coefficient that you had at this point. So here, so the skeleton has the property that for any closed point x, the characteristic polynomial at x depends only on x, not on c. Well, I should say. So if you have any closed point on one of these curves, then the characteristic polynomial of the coefficient that you're considering on x is independent of which curve you're taking that passes through this point. So that's some very strong restriction on these coefficient objects. And essentially what you need to do is use some sort of uniformity properties of coefficients on curves to show that you can actually assemble these things back together. Let me not say more than that because time is short. But so this argument, I should also maybe credit. There's some older work by Wiesand on higher class field theory that is the key idea that goes into it. Somehow the idea that everything can be recovered from restrictions to curves is an idea that's embedded in the work of Wiesand and was kind of teased out by Drinfeld. And it kind of runs through the rest of the board as well. So for P goes to L, for P goes to L, the idea is that you're trying to build some L-adic coefficient. So the idea is you want to run a similar program. So, of course, once you get to the skeleton, then you're basically so you don't really have to do anything new at this step, because if you have an L-adic skeleton that has the right compatibility properties, then you're in the same situation that Drinfeld was in, and you can kind of just run his argument. So the part that requires the work is to show that given a P-adic coefficient, when you that you can restrict to curves and then apply the Langlands correspondence. So this is just making sure that that L-adic arguments carry over or have been suitably replaced. Because some of the arguments don't carry over. This is something we've been talking about, I guess, the last talk I gave in the working group, which was 2 weeks ago, was a little bit about this, the extent to which certain arguments in the L-adic world do not carry over to p-adic coefficients. So for example, the proof that the cohomology of a coefficient object is finite dimensional actually requires a lot of work in the p-adic case that's somehow different than in the L-adic case. But the good news is by the time you know enough to be able to, say, run Abbe's proof, which depends on basically having a full 6 functors formalism in p-adic cohomology, with a small number of exceptions that are easy to handle, you know enough to run this part of the argument. So in some sense, you don't need to know too much. You don't need to do too much new to get from here to here compared to here. Here, you would like to do the same sort of thing with the roles reversed, but we don't. The argument from here to here somehow completely breaks down, because the argument that Drinfeld uses to assemble the skeleton together actually uses, in a very essential way, the fact that an L-adic coefficient object is some sort of representation. So you build this thing you build a mod L representation, a mod L squared representation, and so on, and you kind of fit them together by taking an inverse limit, and then you invert L at the end. There is nothing like that in the p-adic world. So there is no analog of assembling a skeleton using residual representations, because the thing that we're trying to construct is just not related to a representation in such a direct way. However, so let me just draw sort of a cartoon of the picture that comes up. So this picture also shows up somewhere in here, but the basic idea is you use P goes to L to perform many geometric reductions. So this is what I'm planning to talk about this week, actually, is these geometric reductions that will follow from, well, or this week or maybe early next week. This case gives you a lot of geometric reductions. So things like, if you start with some x and you want to construct crystalline companions on x, it would be enough to do it after, say, making some finite cover of x, or shrinking x to some open subscheme, or this kind of thing. So this allows you to eliminate a lot of ugly features of the geometry. And in particular, you can focus on the situation where x is some sort of fibration in curves, which is the complement of some union of sections. So x is here. This is what's called an elementary fibration. So you basically want to induct on the dimension of the scheme x. So you fiber x in curves. The space will have dimension 1 lower. And then you use the fact that both on the Etale side and the de Rham side, when you have this family of curves, coefficient objects in this picture are kind of rigid. So if you have a coefficient object on one fiber, you can, in some sense, sort of spread it out to adjacent fibers. So this is what the process for doing that is something I'm going to be talking about in the next couple of weeks, the next couple of weeks. So you use the fact that, and again, this is used in Drinfeld's argument in some form, but I need a slightly different version in this case because I need to do this on the de Rham side. But so I sort of start with an Etale coefficient object in this picture. I restrict it to this curve. I use the one-dimensional case to make a crystalline companion on this curve, and then I take, say, I break this thing up into irreducibles, and I show that those irreducible pieces can be spread out in some fashion, which isn't necessarily the one that I actually want, but I can sort of compare them to the one I want by taking the crystalline thing that I made. So I spread out the crystalline companion on one fiber. And then move it back to the Etale side to compare with what I started with. And what you end up showing is that basically the only way you end up getting off is somehow by some kind of rank 1 twist on the base. So the spreading out process cannot distinguish between, because you're somehow looking at one fiber, you can't you can't control for rank 1 twists on the base. But in some sense, you show that that's the only bad thing that can happen. And because I'm assuming, sorry, it's not a rank 1 twist. It's some kind of twist on the base. But since I'm working by induction, I know that everything defined on S, or things of the same dimension as S, those things have crystalline companions. So I can kind of correct for that twist. So yeah. So the goal for the next couple of weeks in the working group is to kind of describe the details of this. But for the purposes of this presentation, this is maybe all the level of detail that we should really go into. So yeah. So you kind of break this process of constructing companions breaks into these 3 steps, and this somehow clearly covers all possible cases. So let me stop there.
Thank you.